You're standing on a beach, looking out at the ocean. The waves roll in, crash against the shore, and if you've ever gotten a mouthful of that water, accidentally, or as a kid who didn't believe their parents, you know exactly what it tastes like. Salt. So much salt that it's almost undrinkable. The ocean is famously, undeniably salty. Now imagine you're standing next to a river. The water flows past you, clear and fresh. You could bend down, cup your hands, and drink it without any problem. Sure, it might not be as clean as bottled water, but it doesn't taste like salt. It's just water. Rivers, lakes, streams, they're all essentially fresh water. So here's the question that seems so obvious, it's strange that most people never ask it. Why is the ocean salty, but rivers aren't? They're both just water. They're both part of the same planetary water system. Rain falls on land, forms rivers, and those rivers flow into the ocean. So why does one taste like you're licking a salt shaker while the other is perfectly drinkable? The answer isn't that the ocean somehow produces salt or that seawater and river water are fundamentally different substances. It's the same H2O molecules moving through the same water cycle. The difference is what happens to those molecules over time, and more importantly, what happens to everything dissolved in them. The ocean is salty because it's the final destination in a one-way journey that's been happening for billions of years. Rivers carry tiny amounts of dissolved minerals, including salt, from the land into the ocean. Once that salt reaches the ocean, it stays there, forever. It has nowhere else to go. Meanwhile, the water itself evaporates, forms clouds, falls as rain, and starts the journey all over again. But the salt doesn't evaporate. It gets left behind. And, after billions of years of this cycle repeating, the ocean has accumulated an absolutely staggering amount of salt with no way to get rid of it. To understand how this works, we need to start with where the salt comes from in the first place. When rain falls, it's essentially pure water, distilled by nature. Water evaporates from the ocean, leaving the salt behind, then condenses in the atmosphere and falls back to Earth as fresh rainwater. But the moment that rain touches the ground, it starts dissolving things. Water is called the universal solvent because it's incredibly good at breaking down and carrying away minerals from rocks and soil. As rainwater flows over land, it picks up trace amounts of minerals. Sodium, chloride, calcium, magnesium, potassium, and dozens of others. These minerals come from the slow, constant erosion of rocks. Every time water flows over stone, it dissolves a microscopic amount of material and carries it away. Individually, these amounts are tiny, almost undetectable. A river might contain only a few hundred parts per million of dissolved salts. That's why river water tastes fresh. The concentration is so low that your taste buds don't register it. But here's where it gets interesting. That river doesn't just flow in circles. It flows downhill, following gravity, until it eventually reaches the lowest point it can find. For most rivers, that lowest point is the ocean. And when the river empties into the ocean, it dumps all of those dissolved minerals right along with it. The water continues on its journey. It evaporates from the ocean's surface, becomes clouds, falls as rain, and starts over. But the minerals don't evaporate. Salt, along with all the other dissolved substances, is left behind in the ocean. This is the one-way journey. Minerals flow from the land into the sea, but they never flow back out. Every river on Earth, every stream, every bit of runoff is constantly delivering a small payload of dissolved minerals to the ocean. And this has been happening not for years or centuries, but for billions of years, ever since the oceans first formed. Let's put some numbers to this to understand the scale. The ocean contains roughly 1.4 billion cubic kilometers of water. In that water, there are approximately 50 quadrillion tons of dissolved salts. That's 50 with 15 zeros after it. The vast majority of this, about 85%, is sodium chloride, which is table salt. The rest is a mix of magnesium, calcium, potassium, and other minerals. Rivers add roughly 4 billion tons of dissolved salts to the ocean every single year. That might sound like a lot, but compared to the total amount already in the ocean, it's a drop in the bucket. At current rates, it would take hundreds of millions of years for rivers to double the ocean's salt content. But here's the thing. This process has already been going on for somewhere between 3 and 4 billion years. The Earth's oceans formed not long after the planet itself cooled down enough to have liquid water on its surface, and from day one, this cycle of erosion and accumulation has been running. Early in Earth's history, the oceans were probably much less salty than they are today. Fresh water filled the early ocean basins, and the salt content started at close to zero. But as soon as rivers began flowing, they started delivering minerals. Over geological time, the salt concentration increased steadily. However, it didn't increase forever. At some point, the ocean reached what scientists call a steady state. This is where the amount of salt being added by rivers roughly equals the amount being removed by other processes. Wait, removed? If salt can't evaporate, how does it get removed? The answer is through chemical and geological processes that happen on the ocean floor. Some dissolved minerals react with rocks and sediments, forming new compounds that settle out of the water. Others are absorbed by marine organisms that use minerals like calcium to build shells and skeletons. When these organisms die, their shells sink to the bottom and eventually become part of the ocean floor sediment. Over millions of years, these sediments can be compressed into rock, effectively locking the minerals away. Additionally, in certain shallow, warm areas of the ocean, evaporation can be so intense that the salt concentration becomes so high that salt literally crystallizes out of the water and forms deposits. These salt flats and evaporate deposits remove salt from the ocean, at least temporarily, though much of it eventually gets redissolved when conditions change. The point is, the ocean isn't just endlessly accumulating salt without limit. There are processes that remove it. But these processes are slow, and they're roughly balanced with the rate at which rivers add new salt. That's why the ocean's salinity has remained relatively stable for hundreds of millions of years, even though the one-way delivery system is still running. Now you might wonder, if rivers are constantly carrying minerals into the ocean, why don't rivers get saltier over time? Why does river water stay fresh? The answer is that rivers are flowing systems. The water in a river doesn't sit still. It's constantly being replaced. Fresh rainwater flows in from upstream, picks up a tiny amount of minerals, and then flows out into the ocean downstream. A single molecule of water might spend only days or weeks in a river before reaching the sea. It doesn't have time to accumulate significant amounts of dissolved minerals because it's constantly being flushed out and replaced with fresh water. The river is like a pipe that's always flowing. Minerals pass through it, but they don't build up in it. The ocean, on the other hand, is a closed basin. It's the end of the line. Water flows in, but the only way water leaves is through evaporation, and evaporation doesn't take the salt with it. So while the water molecules themselves cycle through the ocean relatively quickly, on average a water molecule spends about 3,000 years in the ocean before evaporating. The salt stays behind indefinitely. This creates a concentration effect. Imagine you have a bucket with a small hole in the bottom. You keep pouring in water mixed with a tiny bit of sand. The water drains out through the hole, but the sand stays in the bucket. Over time, even though you're only adding a little sand with each pour, the bucket fills up with sand because it has no way to leave. That's essentially what's happening with the ocean. The water cycles in and out, but the salt just keeps accumulating. Interestingly, not all parts of the ocean have the same salinity. The average ocean salinity is about 3.5%, which means that for every kilogram of seawater, there are 35 grams of dissolved salts. But this varies depending on location. In areas where a lot of fresh water flows in from rivers, like near the mouth of the Amazon or the Mississippi, the salinity is lower because the fresh water dilutes the salt concentration. In areas where evaporation is high and rainfall is low, like the Mediterranean Sea or the Red Sea, salinity can be significantly higher because water is being removed but salt isn't. In fact, the Dead Sea, which is technically a lake, not a sea, has a salinity of about 34%, nearly 10 times saltier than the ocean, precisely because it's a closed basin in a desert climate where evaporation is intense and there's no outlet for the water or the salt. There's also the question of why the ocean doesn't just keep getting saltier and saltier forever. If the input from rivers never stops, shouldn't the ocean eventually become as salty as the Dead Sea, or even saltier? The reason it doesn't is because of those removal processes we talked about earlier. As the concentration of certain minerals increases, the rate at which they get removed also increases. Chemical reactions happen more readily, organisms can extract more material for shells, and in some cases, the minerals reach saturation and start precipitating out of the water directly. This creates a natural balance. The ocean reaches a salinity where the input and output rates are roughly equal, and it stays there. Scientists believe the ocean has been at approximately its current salinity for at least the past 100 million years, possibly much longer. Another fascinating aspect of this is that the composition of ocean salt isn't exactly the same as the salt rivers bring in. Rivers carry a variety of dissolved minerals, but the proportions don't match what we find in the ocean. For example, rivers tend to carry more calcium relative to sodium than ocean water contains. This is because calcium gets removed from the ocean much more efficiently than sodium does. Marine organisms use calcium to build shells and coral structures, and calcium also reacts with carbonate in the water to form limestone sediments. Sodium, on the other hand, is much less reactive. It mostly just stays dissolved in the water. This is why sodium chloride dominates ocean salt composition. It's not necessarily that rivers deliver more sodium. It's that sodium has no good way to leave once it arrives. The one-way journey of salt from land to sea also has massive implications for the water cycle and life on Earth. If the ocean were fresh water like rivers, the entire planet's ecosystem would be completely different. The salinity of the ocean affects its density, which drives ocean currents that distribute heat around the globe. It affects what kinds of organisms can live in the ocean. It even affects the freezing point of seawater, which is lower than fresh water, meaning the ocean can stay liquid in conditions where fresh water would freeze. The salt in the ocean isn't just an interesting quirk, it's a fundamental property that shapes climate, weather, and the biology of the planet. So when you stand at the beach and taste that salty water, you're tasting billions of years of geological history. Every grain of salt in that water came from somewhere. It was once part of a mountain, a rock, a grain of sand somewhere on land. Rain dissolved it, a river carried it to the sea, and there it stayed. The ocean is salty, not because it started that way, but because it's been collecting the dissolved remnants of the continents for as long as water has flowed downhill. Rivers aren't salty because they're just passing through. They're delivery systems, constantly moving, constantly refreshed, never holding onto their cargo long enough to taste it. The ocean is the vault at the end of the line, where everything ends up and nothing leaves. It's a one-way journey, and after 4 billion years, the vault is full of salt. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution.